Ladies and gentlemen, good morning. I am Hashmi Garrot, professor at the Higher School of Computer Science in Algiers. It's my great pleasure to talk to you today about highlights of our work entitled 3D brain image segmentation model using deep learning and hidden Markov random fields. This presentation is organized as follows. We begin by introducing the problematic, followed by some concepts on hidden Markov random field and deep learning. After that, we will talk about hidden Markov random field deep learning combination, followed by some experimental results. Finally, we will give conclusion and perspectives. Let's begin by introducing the problematic. Nowadays, we face a huge amount of data produced by imaging devices. The manual analysis and interpretation became a tedious task. For that, the necessity of a good segmentation system in order to help physicians hold easily the final decision. Hidden Markov random field. In hidden Markov random field, the pixels values are considered as realizations of random variables, where the pixels in image to segment or observed image y take their values between 0 and 255, that means degree level space. And pixels in segmented image or hidden image x take their values between 1 and the number of classes k. So, hidden Markov random field is looking for the perfect segmentation x star which maximize the probability given in the following formula. This elegant model leads to optimization of an energy function given in the following formula. Our way to look for the minimization of this function is to look for the minimization of the same function in function of means instead of x and y. The main idea is instead to look for the perfect segmentation of x, which minimizes the function psi. We look for the perfect centroids or means that minimize the same function. Let's now talk about some concepts of deep learning. Deep learning is used to generate a powerful model that takes data in input and use it to predict a good solution in the output. Deep learning algorithm is a set of interlinked layers that form what are called neural networks. The first layer called the input layer, the last layer called the output layer, and the layers between them called hidden layers. Layers are composed of nodes that use tunable parameters, width and bias. The success of model highly depends on the performance of the training stage. Through the large dataset of input and output pairs, a deep learning network tries to minimize difference between its prediction and expected output by adjusting the width and the bias parameters. The input of our model M, which represents the centroids of partitioning the image y into k classes using the function k-means. AG and BG represent the two parts of psi when we use centroid MG. Mu hat and mu star represent respectively the predicted outputs and the expected outputs. After the training process and generating the deep learning hidden Markov random field model, the segmentation program can be schematized as follows. We use k-means to have centroids that represent the description of an image. Using these centroids to compute AG and BG that represents the inputs of our model. After that, we will have mihat, where we will use it to get our segmentation. Experimental results. In order to evaluate the segmentation quality, we use dice coefficient criterion. Dice coefficient measures how much the segmentation result is close to the ground truth. Where the dice coefficient equals 1 in the best case, dice coefficient equals 0 in the worst case. In our implementation, we have used Python as a programming language. i7 capable computer with the Windows 10 as operating system. We have used EBSR images in our tests and also to prepare training datasets. They are 20 3D brain images where the ground truth images are available. We have dedicated 14 EBSR images to train our model. The rest of images, that means 6 images, are devoted to the tests. Our proposed architecture is based on MLP. The generated models for the number of classes k equal 3. That means our model segments to 3 classes: gray matter, white matter, and CSF. The performance of MLP depends on hyperparameters values. For that, we have made many tests to select the values shown in the table that give suitable metrics. The performance of our model is very sensitive to hidden Markov random field parameters that are b over t and the number of neighbors. In total, we have created 6 models with different value of parameters. Through the results, we have noticed that the training time is considerable and the model with these parameters give generally the best results. For that, there is many well-known and powerful application in brain image segmentation field like FreeSurfer, SPM, and FastFSL. We have noticed that they give good segmentation with slight differences. For that, to simplify, we have compared our model with the best parameters with the last release of FastFSL application. Through the results, we noticed that our model generally gives the best results. Here we present some visual results where it's clear that the result of segmentation using our model is near to the ground truth segmentation than FastFSL application. Through the achieved results, we could say that our model deep learning hidden Markov random field is very promising in quality of segmentation. Nevertheless, the training time is still considerable. As perspective, Kubernetes cluster can be used to reduce training time. Thank you for your attention, and I am looking forward your questions.